Good morning. I'm Liam Viñales. Great freedom to how to operate them. But that means that we have to make decisions. For instance, in the thermal units, we have to make the decision of what power should it generate, and we have to consider their costs, that they may be non-linear costs, or the cost function may not be constant over time because it may depend on variable factors. We have to consider also that the minimum power of thermal units is high, so we have the decision of shutting it down or not, etc. We then have renewable generation. In a normal operation, we would like them to search the maximum power point, but in some cases it may be interesting to curtail some of the power. It can be because we have underestimated the renewable generation in our participation to the main market, and then we do not want to deviate in our common coupling point. Or it can be because we cannot rely too much in renewable energy, because we may have some stability issues, especially if we are in islanded mode. We then have the energy storage unit. This unit has a very large installation cost, so we have to operate them to make up for these costs, and we have to decide when we should draw the energy from the grid and when we should generate it. And then I have included here two kinds of special loads that are shift-level load our electric vehicles, and these are loads that we can choose where to start satisfying them, or we can choose how do we want to use the energy in the case of the electric vehicle, provided that we, at the end, when the electric vehicle leaves the charging point, it has a determined state of charge. Moreover, we have the decisions regarding the main market. We have to make offers and bids to the market, and this is critical for the profit of the microgrid operation. And during the real time, we have to choose whether we may deviate from our contracts previously traded in the market, or it is better to change our configuration and do not deviate. So we have a lot of decisions. If we include more renewable resources or more units, we would add more decisions. So it's quite a complex problem here to solve. And we want to make those decisions in an optimal way from an economic point of view. But besides of that, we have some constraints that we have to satisfy. These constraints are very different in islanded modes or grid-connected modes. In grid-connected modes, they are more relaxed than in islanded modes, and that we have to make sure, as my colleague said, we do not have the voltage profile in this grid, so we have to make sure that the voltage limits and the lines are not saturated and the voltage limits are not exceeded. We have to include somehow the network model to anticipate the voltages and operate the units according to that. Moreover, we have our microgrid connected to the main grid. This means that we may have a TSO or a DSO that may give us some requirements in terms of run rates that we can perform in the common coupling point, or maybe reactive that we have to inject. So we have also to consider the TSO requirements during the operation in grid-connected mode. When it comes to the islanded mode, here we do not have the bus to handle imbalances in power, so we have to create the network ourselves. We have to guarantee that our voltage and frequency are stable, and stable versus the variability in both renewable generation and consumption. Moreover, we have to detect faults of the main grid and quickly disconnect, as it has been said, and then resynchronize. So basically we have some decisions that have to be made during the operation of the microgrid, and we have some constraints that must be satisfied. So another issue in microgrids is uncertainty. consumption introduces uncertainty, and so does renewable energy. And it also market prices can be considered uncertain. And we deal with uncertainty with forecast algorithms. We have medium-term forecasting and short-term forecasting algorithms. But these algorithms, in the case of microgrids, always have error, because it is not possible to predict properly the consumption and renewable generation, as I will show in the next slides for an example. So, having uncertainty means that we do not know the actual power flow that will appear in our grid until it does. But we want to make some decisions in an optimal way, and this takes time. And we cannot continuously make the optimal decisions, so we can split these decisions in two different categories. We have planning decisions that are smart decisions but based in forecast, and then we have the real-time operation decisions that are based in local measures. So here we have an example. This is a real 10 megawatt example microgrid. This is the consumption profile in a resolution of seconds. We can see that in general it is a very noisy signal, so we can tell in advance that we want to get rid of this variability here. And moreover, we can see that there are huge drops in power in just a few seconds. These drops does not follow any pattern over time and are absolutely not possible to predict. If we look then generation, there is a huge difference between when there is a clear sky and then the variability is very low, but once there is clouds, this is just random changes in renewable power generation. So this cannot be forecast either. We can somehow estimate the variability, but we cannot precisely define the power available. The forecast technologies that we are using in order to forecast these two signals are based on time series and machine learning. And these strategies, what they do is they look for patterns and some regression with other variables. And these systems work reasonably well for aggregated consumption for our country, for instance. But with disaggregated consumption, they do not give good results. So we have to deal with errors, and we cannot have better forecast, at least in the near future. One good thing that these technologies have is that they provide us not only with an expected value, but with a shape of a distribution function that we can use in order to make decisions, so that we have not only an expected value information, but also variability information. So, how can we make decisions under uncertainty? The hierarchical control is proposed, and it consists of defining 3 different levels of control. We have the first level, which is the inner loops of the converters and synchronous machines. And we can also add local controllers if we are worried about any communication loss, because the level 2 and 3 are centralized and they require communications. So the level 1 can have local controllers and consist of the inner loops of the converters that they make that the converters and the different units can follow the power references that we have. The level 1 is the faster control, and it is eventually what determines the microgrid operation. On an upper level, we have level 2. It is centralized, is what we call microgrid controller, and is responsible for sending references to different inner loops in the level 1. This is also continuously executed. It's a control loop, but it is slower than the other one. And finally, we have the level 3, which is executed every minute or minutes, every few minutes, and it is where the planning decisions are made, and we send power references to the microgrid controller every 2 minutes, for instance. So here I will explain a little bit the responsibility of each level of control. The upper level, or level 3, cannot decide the actual power balance because it doesn't have this information, but it can decide other variables such as switching on or off thermal units, managing dispatchable load, etc. Moreover, it can decide how the microgrid controller should act in grid-connected mode. That means that the level 3 can program dynamically the microgrid controller and teach it how it has to act against power imbalances. And it is computationally expensive if we compare it with the other two, in the sense that it must be executed and it may take minutes. It depends on the size of your microgrid and the complexity of your model. The medium level is centralized, it's the microgrid controller, and cannot take decisions, but it only applies simple rules. It continuously applies the same rule with the data that it has. In grid-connected mode, it follows economic criteria, as I said, is programmed by the upper level, but in islanded mode, it follows just stability purposes. The lower level, from the point of view of the energy management system designer, it's a parameter. I mean, we assume that the converters have inner loops that may follow our references, but this is given by a manufacturer. I will go into detail of the lower levels, the level 1 and level 2, for both islanded mode and grid-connected mode. In islanded mode, the lower levels are responsible for creating the grid. As it has been said before, we have an element that must create the grid. It can be the battery or maybe a synchronous machine. And the other converters are acting as current source converter. And we need something that is called a load sharing strategy. Because if we don't have load sharing strategy, if there is a power imbalance, the element that is creating the grid must somehow compensate all the imbalance itself until the microgrid controller can see and send new power references to the elements. This can have issues. For instance, if it is a synchronous generator who is generating the grid, maybe itself has a too slow response against for instance, a big change in consumption, and this may bring our frequency in levels that we don't want it to be. And if it is the battery may be over-discharged or overcharged depending on the power imbalance. So we need a load sharing strategy, which means that we take all the different elements of our system and we make them all act if there is changes in consumption or generation. I will present here, there are many load sharing strategies. I will introduce the more straightforward, which is the droop control. And it basically, what it does is each unit, we program a response, immediate response versus changes in voltage and frequency. For instance, here we have the droop control, which relates frequency and active power, and it means that that unit, if there is a change in frequency, must immediately the reference of power changes according to the droop curve. Doing this, when there is a variation, each element operating the microgrid contributes proportionally to the curves, and we can share the power imbalance between all elements from second zero. We don't have to wait for the microgrid controller to see the power imbalance and then try to modify the power references. Then this droop control can be corrected once the power imbalance is stable and it is done by modifying dynamically the Droop's curves so that we can achieve more similar solutions to what we were looking for by our references. Because in the Droop control, we may get some configurations that we do not want in a steady state. For instance, the conventional generators may generate a lot more. It is good to provide a fast response, but we don't want it to be in a steady state generating that much power. So that's the islanded lower levels controls. Is there any question about these controls? I will move. This is the grid connected control. Here we don't have the stability issues that we have in islanded modes. So here the microgrid controller is more simplistic. It's what we call a dump unit, that it only continuously applies the same rules, and it also has to handle the TCO demands. Here it receives from the level 3 of the control references and what to do in case of imbalance, and it sends references to the converters, acting like just a dump unit. For instance, the information that this unit may receive is PV reference, thermal unit set points, and moreover, in case of imbalance, battery should generate drop source. That's the kind of information that this unit receives. So we have seen the lower levels, and we will now move into the third level, the economic one. This is where the smart decisions are made. And there are two possibilities that are very different. We can have single owner microgrids. That means that there is one owner of all the different elements, and here the load must be satisfied, and it is a cost minimization problem. We know exactly what the generation costs are, and the profits are shared among all participants of the network. On the other side, we may have different owners, and these owners compete with each other in order to generate their energy and to consume the energy. So when there are different owners, we have to adopt a market strategy, or it is also called local market strategy, micro market. It has many names. And it consists of sorting the offers. This is, I hope that you have all seen the market clearing model, but it is about sorting the offers and trying to maximize what is called social welfare. So this is a maximization problem, not a cost minimization problem, and it is of a different nature. The single owner model is useful for small microgrids and for microgrids that are always islanded. When there are grid-connected microgrids of a larger size, the single owner model is not realistic. Here we will look at how the optimization problem works for islanded microgrids. And as I said, in these cases, single owners models are assumed. And it is a minimization cost subject to that the load must be satisfied and the stability must be ensured. That means that this constraint, the stability must be ensured, we have to model it in a mathematical programming manner. And it's not easy. But you have to manage to formulate it in an optimization problem. We have to define a worst case scenario that we want our system to be able to support. That optimization problem would mean, for instance, that you want to maximize renewable generation, but without compromising stability in your grid. That means that if you allow more photovoltaic power, you may face bigger changes, and you may not be able to guarantee stability, so you may not want to generate that much solar power, or you need more inertia, so you turn on some synchronous machines that it wouldn't have sense to turn on in other situations. And for grid-connected systems, the upper level have a similar aspect like this. We have two different problems. We have first the market bidding problem, which consists of participating in the main grid markets. We have to decide what offers we present and what bids we present in case that we want to consume or generate energy. This is done with middle-term forecast, which has huge error. So we need another optimization problem, which is what I called here online algorithm. Can also be seen as a corrector that with the short-term forecast can correct and take these planning decisions. These optimization problems need to model the microgrid, and here you can add more complexity to your model, or you can use models that are simpler. For instance, you can just take a linear model and go forward, or you may have to consider convex cost generation or the unit dispatch problem. You can add the network equations if you want the flow to be performed. You can add the converter equation, the battery usage cost, etc. Moreover, you can take into account uncertainty and your optimization problems. Uncertainty means that your problem size is growing exponentially. So if you want to take into consideration uncertainty, you have to have simpler models of deterministic optimization problems, because otherwise it is hard to solve. So there is a trade-off usually between better uncertainty characterization and better model of your microgrid. So here my recommendation is that you only increase the complexity of your model if you are sure that a simpler model cannot represent your real system. But this is very dependent on the actual system that you have, and moreover, it can only be seen by simulation, so it's tedious work. Here I present the link that there is between the market bidding problem and the online algorithm or corrective algorithm. The market bidding problem determines the energy that must be exchanged each hour. That means that straight line here. But it only matters that at the end of that hour, that energy is delivered. It doesn't matter the specific profile. So the online algorithm is seeing, for instance, that generation, and he has to estimate whether there is a potential deviation and correct it dynamically. For instance, here we would have a potential deviation, so we would have to increase generation somehow to try to match the market bidding offer, but in that case it's okay because we have at the end of the hour delivered the energy. And this link is used for explaining how optimization is considering uncertainty, and the field of optimization that considers uncertainty is called stochastic programming. That means that you have two problems that are linked in time. So here we have the market bidding problem, and is linked in time with the online algorithm. We can formulate this problem in order to take into account this link. And it is done with the following rules. You have your benefits from the market that you include here in your objective function, and it is common for all the scenarios. Then you generate a bunch of scenarios that are possible, and with this market bidding problem solution, you then can solve the online algorithm for each scenario. And you can include an average of these online algorithm costs here, and it represents the expected value of costs for each decision of the market bidding problem. This way you can optimize at the same time the marketing problem considering the online algorithm. And finally, some conclusions. islanded and grid-connected systems has nothing to do with each other, but you have to design both if you want a microgrid capable of switching out. The hierarchical control is a good approach, but you have to define these 3 levels. And it's not probably the best solution that will be found in the future. Decisions may be taken under uncertainty, which makes it much more difficult. And the control and the energy management system is really dependent on the actual element of your microgrid, so it does not make any sense to try to find generic solutions which are prohibitively complex. And you have to stick to what your real projects are, because in some cases the solution may be trivial or much easier. And it is a challenging and yet to be defined area, and that's all. Thank you for your attention.